Hello everyone, I hope you can hear me now. I will be presenting results we obtained for subtask 3. I first have to thank all the participants. We were a nice group of people who really dug into the cases and studied the applying of analysis methods on these cases. It was a group which regularly met, so also in between the 2 yearly meetings, we gathered regularly to discuss results. So it's because of the participants that we were able to deliver this report. So thank you for that. Subtask 3.
I can't see your slides in presenter mode. Can you put them in presenter mode?
Oh, sorry.
Yeah, that's perfect. Yep, great.
Okay. Subtask 3 is about assessing the thermal performance of the building fabric. So it's, as Richard already mentioned, it's a heat transfer coefficient, but in a way that is reproducible and repeatable. So we want to apply these on real buildings and be confident that the result is that we can use the result to inform a strategy. And we want to do that when for buildings when limited monitoring data is available. So these are the presets going into this work. To do this, we apply statistical methods which are inspired by building physics. So either we, as you see here on the right, we actually chop up the building to different pieces with resistances, capacities that kind of simulate or model the heat flows that occur within the building and towards the outside. As I said, we organized 2 yearly meetings where all of the Annex participants came together. But in between the meetings, we every one or two months we gathered with a subtask 3 task force to continue our work and discuss our findings that we obtained in the meantime. And it's because of that we came up with quite a comprehensive report, which is structured in this way. So I'll briefly go through it. So to understand what we are doing, we begin with a kind of a building physical framework. So we look at what is happening in the building, how are we describing the thermal dynamic behavior of the building. I will go to the next slide. So this is the first part of our report, and we kind of lay out the heat balance of the building to be sure that we haven't missed anything, and also to, when in a later stage we use simplified models to model the building's thermal behavior, that we can be confident of the results that we obtain, that we know what is lumped into the different parameters that we are estimating. So it will help us interpret the reliability of the estimated parameters and the uncertainty that we need to take into account there. So there's many issues or aspects that come into play when looking at the thermal behavior of a building. We have the heat input from the heating system. We have internal heat gains from users, solar heat gains, latent heat that plays a role, transmission heat exchange towards the outdoors, towards the neighbor and towards the ground. So there's many aspects that come into play, and this first chapter lays these out and makes sure that we don't miss anything going further. In a third chapter, we look at the statistical modeling approaches. So what methods can we use to analyze the data and to get physically relevant parameters out of it? And there's two methods we can distinguish. First we have the static methods, where we neglect the dynamic behavior of the building. So we, for instance, look at a longer period. We even out all the dynamics that take place and look at the parameters that come from out of that. And then you have the dynamic methods, where we explicitly model the dynamics of the building. So first, the static methods. So you have the simple average method, where you just take the mean of the heating power divided by temperature difference between inside and outside, and you get an estimate of the HTC. So it's a very simple method, but for instance, you cannot say anything about the impact of solar gains on the building. So it's a very simple method, where we do miss some things that are important and that are significant to explain the building's behavior. The second method is a linear regression analysis, where we fit a linear line through the points, and it allows us to not only estimate the heat transfer coefficient, but also the solar aperture. So it allows us to say something about what solar gains can we expect when we know the solar irradiance hitting the building. A final static method is the energy signature method, which is used to analyze energy consumption data, and it allows you to get an estimate of the heat transfer coefficient and also the base temperature. The base temperature below which you will start to heat the building. Dynamic methods. So there we have three methods that we can distinguish, which are all dynamic. So you have first the white box tunings, essentially using a simulation model and tuning the parameters so you get a fit to the measured data. In Subtask 3, we don't dive deeper into that. It's the working group of Paul Strachan and Matthias Kersken that look at the validation exercise. We look mostly at the ARX and RMAX modeling, so black box modeling. It's a purely statistical method that comes up with some parameters, and in the next step we can compare them to physically relevant parameters. The state space models, finally, they are interesting in that they are a direct translation of physically relevant parameters into a simplified model. So you see an example of that at the bottom right of the slide. So you essentially, whereas if you want to explain the building's dynamic thermal behavior completely, you would have a distributed set of thermal nodes, infinite number of them. But what we do here is we limit the number of thermal nodes, and we explain the heat exchanges that occur between them, the amount of heat that the different thermal nodes store, etc. So it's a simplified model which lumps the different physical aspects that come into play in a more simplified way. So the next chapter looks at the input variables. So there's many, as I said, many things that come into play in the heat balance. There's many things we can measure. So the idea of this chapter is looking at what are the input variables that we would have available, what is important to have available, and what is less important to have available as an input to our models. So it looks at first solar gains. So for each of the input variables that we look at here, we have some approaches that we look at in detail. So the first approach for solar gains, for example, would be to not include it in the model, so to neglect its impact. Another approach would be to assume a constant solar transmittance, so that the solar gains are actually a constant times the solar irradiance touching the facade. Then you can also have constant solar transmittances for each of the cardinal directions, which is a bit more complex, but more or less similar to the previous one. And then the figure illustrates the result of that. You have the spline-based approach, where the goal actually is to take into account movement of the sun elevation, and to model the impact or the solar gains that result from that by using a superposition of splines throughout the day. So for each orientation you would have a spline, and the final solar aperture that you calculate throughout the day is a kind of a weighted average of these splines. So it's a much more complex method, but we see that when, for instance, prediction is important, when you want to predict something with the model you estimated, then these more complex approaches become important. Heat input, so of course that's a very important input to our model, and there we distinguish between, are we measuring the inputs before the generator or after? So are we looking at gross energy consumption or net energy consumption? And do we have a separate idea of the energy that is used for space heating and for domestic hot water? So depending on that, our results will become more or less reliable. Then infiltration and ventilation heat loss. So we have a ventilation heat exchange through the fabric via mechanical ventilation, but also through by means of infiltration, exfiltration through the fabric. So this chapter is looking, or this part of the chapter is looking at what are the simplified models that we can use to model it, and how can we, for instance, split the heat transfer coefficient that we are estimating as part of the modeling into a part that is due to transmission through the fabric and a part that is due to infiltration or exfiltration through the fabric. Then we have, of course, the occupant and appliance heat gains, which looks at using standardized occupancy profiles to model internal gains, or using measured relative humidity and CO2 to estimate internal gains. And it also looks at the impact of lighting and other appliances generating heat inside. And then weather data, as you all know, gathering weather data on site is often a complex affair. It's also costly. So this part of the chapter looked at what are alternative data sources to use to inform the model. So more and more you see national weather stations releasing detailed weather observations and climate information, which is more and more available free of charge. And you also see on the EU level climate reanalysis initiatives that combine modeling with monitoring of weather data to actually come up with a kind of fine-grained weather model, so that depending on where you are monitoring, where you are assessing a building, you can use these reanalyzed data sets to have quite reliable weather data on site or near your site. Then indoor temperature, so often there is no measured data available. Sometimes you have thermostats which you can use the data from. So here in this part we look at the case where we don't have any data available until the case where we have a lot of data available. So for some of the case studies, we have indoor temperature measurement at different heights in the rooms in all of the rooms. So there's we can use in this annex work, we used a lot of data, but we also built down to what happens when we don't have that much data available, and what happens when we, for instance, need to use standard assumptions from SAP or other EPC guidelines. So the next chapter is just outlining the different case studies that we looked at. So we had 5 case studies that we looked at in detail. First, you have the twin test houses in Fraunhofer or in Holzenkirchen, which are monitored in a very detailed way with a perfect control of internal heat gains due to appliances, but also due to occupants, which in this case were simulated. So we simulated the physical appearance of occupants. Then the next case we have Uccle test house, which is inhabited house, which was monitored for over a year in a very detailed way. The particular aspect of this case is that it's a semi-detached house, so there are some uncertainties that result due to the fact that we have a shared, that we have a party wall. Same goes for Loughborough. The difference there is that it's really a test house, so we control both of them, and also here we have simulated occupants. So we simulated by opening up the windows following a certain regime or generating internal heat gains. And then the final case study we analyzed was Gainsborough, which is also an inhabited house, where we also have the issue of the party walls. So in earlier chapters, we looked at the different input variables that we can take into account when modeling the energy performance of the houses. So we end up with a bag full of simplified or more complex approaches that we can apply on these case studies. So in this chapter, we looked at what is the impact of the different approaches. So how do, for instance, the different approaches for solar gains compare to each other? What is the difference that we introduce by looking at one approach or the other? So it was relative. So we didn't look at what are the reference values of the house. We looked at the relative difference between applying the different approaches for each of the aspects. The aim was there to come up with quality procedures and clear guidelines. So what is most important to take into account, or what are the aspects that, regardless of the modeling approach that you apply, are not that significant. So we wanted to highlight those modeling approaches that are really important to get right, and the others that are less important to get right to obtain reliable results. So the same, we go through the different input variables that we identify to be important in the beginning. We zoom in on each term of the heat balance and look at what is important and what is less important. So first application is, or first thing I want to show here is the solar gains. So I will not go into detail, but it's mostly to show you the kind of graphs that we used throughout the report. So I advise you to read the report, as you will see a number of these type of graphs taken in there, looking at the different aspects that I mentioned earlier. So for instance, here you have 2 rows of graphs. So each of the case studies is a row. So for instance, the first row is twin test house N2, and the second row is twin test house 05. So there are 2 test houses on this site. The different columns show you the different analysis methods. So on the left you have linear regression method 2. In the middle you have ARX modeling, so dynamic black box modeling, and on the right you have state space modeling. So it's the gray box modeling, taking into account the physically relevant parameters. One thing we see from this graph is when you go to approach 1 to 2. So each of the 6 graphs that you see here, they have a along the x-axis. You have numbers. So these identify the approaches that we took. So for instance, approach 1 is neglecting solar gains. Approach 2 is assuming a constant solar transmittance and assuming only one input for solar irradiance. So you see that going from approach 1 to approach 2, for instance, in the case of ARX modeling, you see that the estimate for the heat transfer coefficient increases, which is logical, because when we ignore the solar gains, we effectively underestimate the heat transfer coefficient. So I advise you to go through the report and look at the different input variables and the graphs that we generated for this. And I will just highlight some of the conclusions that we got from doing this exercise. So applying these different approaches on the different case studies. So we see that of course the heat transfer coefficient often benefits from including solar gains. We also see that just including a constant solar transmittance often suffices for our purpose, so for estimating the heat transfer coefficient. But for more accurate predictions, if you want to use a model for doing prediction, we would advise to use the more detailed approaches. So we obtained similar results for the heat transfer coefficient, but when we used the models to predict the more complex models, so including spline-based approach to model solar gains, were performing better. Heat input, of course, is the most important term to get right. So the differences between using the different approaches was up to 100%. So that is the most important one. But also ventilation, heating power, heat input due to lighting and appliance heat gains were shown to have a significant impact on the heat transfer coefficient. Internal heat gains due to occupancy was shown to have little impact. But of course, there we have to look at when the buildings are very well insulated, the impact of these internal heat gains will increase and will need to be looked at. Last advice is to include at least one temperature measurement. So we see that the impact of not having a temperature measurement and having to use the normative values instead of a real value has a significant impact on the heat transfer coefficient. Then chapter 7 is it's a different approach. So the last chapter looked at applying for each of the aspects or for each of the term in the building's heat balance, what the impact is of applying different approaches on the case studies. Here, this chapter looked at the different case studies. So it begins with the case studies, and for each of the case studies, given our expert knowledge we obtained, identified the best approach to assess the heat transfer coefficient. So this chapter looks at the different case studies and tries to come up with the best results that we deem possible for the case. And this is also, again, just an example of the results that we show in the report. So this is for twin test house and 2. And the different columns show you the different statistical analysis methods. So you see that the average method, so the very simple methods perform quite well when comparing them to the reference value. So the reference value is the bold line here, and the 20% uncertainty around it are indicated with the dashed lines. So you see in this case that the more simple methods work quite well. That when we apply linear regression and ARX modeling, that we tend to overestimate the heat transfer coefficient, and that when we apply the more complex modeling, in this case, we approach the reference value very well. So also from this exercise, so applying the best approaches to the different case studies, we've collected some guidelines. So as I said earlier, ignoring the solar heat gains will result in an underestimation of the heat transfer coefficient. What we also saw is that without separate measurement of the domestic hot water demand, we tend to overestimate the heat transfer coefficient. What we also see is that many of the modern day ventilation systems are equipped with sensors that allow us to determine the gains and the losses that result from ventilation quite accurately. So it's beneficial to include it in the model. As I said earlier, correct assumption of internal heat gains due to occupants becomes important when the buildings are well insulated. And again, at least one temperature measurement should be used when assessing the heat transfer coefficient. So the final chapter is looking at, so with all of the knowledge that we built up in subtask 3, the aim was to organize a blind test on the SMETR test cases. So many of you will know these test cases. I will not go into detail on the building itself. I think David will touch upon those in a next presentation. But what I will highlight is the assumptions that we made. So we did some pre-processing before we handed over the data to the different participants. The different participants were not aware of the reference value, so they were not aware of what value they were aiming for. They were just asked to apply the best method possible. So we used 30 days of measurements from February 7 to March 8. The solar gains or solar aperture value was estimated individually by each participant. We used gas measurements and the calorific value of gas and an average seasonal efficiency of the boiler to come up with the heat input, power input. The domestic hot water was not measured separately, but we decoupled it based on a method that is laid out by Bakker, Peter, and his colleagues. It was not possible in this case to separate natural ventilation losses from the heat transfer coefficient, and we neglected metabolic heat gains due to participants. So these are the results that are obtained by the different participants. So in this case, for each of the graph, you will see on the x-axis some numbers. In this case, these are not approaches, these are participants. So you have all of the participants applying the same method, essentially. And what is interesting about this result is that you see that for the more simple methods, there's the results of all participants align very well. So, but as the methods become more complex, and it was a point raised by Mr. Novakovic, when there's more technology, there's more room to make errors. So, and you see it clearly highlighted by this graph. When you go to the more complex methods, there is more difference in the assessments made by different participants. So finally, I think the statistical tools that we investigated in this subtask show promise to determine the building's heat transfer coefficient reliably based on limited data. But we need to make careful assumptions with regard to the heat balance terms that we take into account and which of the input variables that we have available in a reasonable way. So it's important to select appropriate modeling approaches and to follow the guidelines and be inspired by the examples that we show in the report when applying this in practice. Finally, I think in this work we applied different modeling approaches on a limited number of case studies. So I think to make the step towards practice to inform norms based on this work, I think it would be good to have to be able to apply these assessments on more case studies, on a large array of case studies. And I think what we did in chapter 8 on the meter test cases was a first step in that exercise, I think. So that's it for me. And if there are any questions, I think we can take them up a bit later today. Thank you very much.